There we go. So we always start with this whole concept of the tangent line and secant line, and I'm including it for the purpose of our notes and just a review on the definition in case anyone needs clarification. So a tangent line, again, is a line which touches a curve at one point only without crossing it. The tangent line touches the curve at one specific point. This is known as the difference quotient when we're talking about the secant line. We're considering 2 points that are close together for the secant line, whereas for the tangent line, we are moving closer and closer to the first point, and we call the formula for the tangent line. Notice that there's a limit right here, which is not present in the secant line formula. We're taking the limit as h approaches 0, and this is known as first principles. Okay, a more formal definition where m of the limit of h approaches 0 using first principles is the slope of the tangent line to f at a given point. We are going to be covering some examples when we are considering the slope of the tangent line at a given point. I have a number of examples to go through today, and I will try to give you some time to copy. So this is a real summary to help you review right before you enter your test. So the limit of the difference quotient has two meanings. We've covered the meaning that it's a slope of a tangent line to y is equal to f of x. It's also the instantaneous rate of change with respect to x. So WRT means with respect to, if you ever see that in your textbook or unit guide. Since these concepts are so important in calculus, the limit of the difference quotient has its own name and notation. The derivative is denoted as f prime of x sometimes. Sometimes it's dy over dox, and I have a slide that covers all of that. The derivative of f of x with respect to x is f prime of x of first principles. And so we are going to talk about the different variations and how the derivative is written because notation is extremely important in your calculus course. So if the original function is written as f of x, then we say the derivative is always f prime of x. If the derivative is written as y is equal to a particular function, then we call the derivative dy over dx. dy by dx, that's called Leibniz notation, and you can research a little bit more of Leibniz and his contributions to calculus. Now, we can always also say that, for example, if you have y is equal to 4x squared, we can take the derivative of 4x squared, and we will find that it is 8x, and you can denote that as d over dx, the derivative of 4x squared. And so it's just a few different notations. I am going to briefly review some things that we defined continuity yesterday, and we determined that the function is said to be differentiable at x is equal to a if f prime of a exists. Now, the common ways for the derivative to fail is a cusp. We looked at that at the last example. I think it was a radical example where we had a cusp. So it is possible to have multiple tangent lines at a cusp, but when you see a cusp in a function, often the derivative f prime of a is going to fail at the point where x is equal to a, for example. We also covered when there's a vertical tangent. Oh, that was the example yesterday, a vertical tangent. The slope m is undefined when we have a vertical tangent, so therefore the derivative is also undefined. And when we have jump discontinuities, so remember, some removable discontinuities are okay, but the derivative will fail with a jump discontinuity. Okay, so one such example, I'm going to reveal this slowly. So see on the left-hand side, we have our graph, the absolute value function, which you definitely explored in your MCR course. There's a sharp cusp when at the point x is equal to 0, y is equal to 0, the origin, and we automatically know because of that cusp, the function is not differentiable at x is equal to 0. Now we can prove this using first principles by substituting 0 plus h and f of 0 into the equation. And we are going to find that as we approach that function from the left or the right, when we approach from the left, the intended height of the function is going to be -1. But when we approach from the right, the function is going to be +1. And therefore the limit does not exist. And f prime of 0 does not exist as well. So this is just an example of why the absolute function is not differentiable. That means that we cannot find the derivative when I say that it is not differentiable. Now this is an example of a function with a radical. F of x is equal to the square root of x plus 2. Now you will notice when you're doing your unit work that conjugating the radical can sometimes be a complex concept for some people. So we always start when we are asked to solve. Remember, there's some cases where you can go into direct substitution, but when you are asked to solve by first principles, that is what I focus on in my lesson because it tends to give students the most trouble. So we start with the first principles formula, and then I substitute the square root of where I see x, I'm going to substitute x plus h into the formula. And where I have f of x, I can substitute the function just the way it is, all over a denominator of h. Now, my radical is in the numerator. That means I need to rationalize the numerator. So I'm multiplying by the conjugate. This gets more tricky when you have, and you had a question in your unit guide on this, when you have radicals in the numerator and the denominator, then you have to rationalize both. But here we're just rationalizing the numerator. Now, this is straight FOIL, and it's a difference of squares situation. So what I'm highlighting in yellow now, that's going to eliminate the radical. This whole concept of conjugating is designed to eliminate all the radicals in the numerator. So straightforward, when you do FOIL, you'll find that this is equal to x plus h plus 2 minus x plus 2. Make sure to keep the second part in brackets, because if you don't, and if you forget to distribute the negative, your answer is going to be incorrect. Now, we do have the radicals in the denominator right now, but that is going to be eliminated when we apply our limit. We haven't applied our limit yet. What we do have to do is simplify the numerator, and when you do apply the distributive property, you'll notice that the x's cancel each other out, the 2's cancel each other out. So I'm left with an h in the numerator and the h in the denominator. Now those can simply cancel each other out like that. So I'm left with 1 over root x plus h plus 2 plus square root of x plus 2. Now at this point, wherever we see h in the radical, we can replace that with 0 and solve accordingly. So this is just straightforward algebra. So I have a slope of 1 over 2 root x plus 2. That is also the derivative. Okay, for a straightforward quadratic function, There may be equations in your unit that look like this. Find the equation of the tangent line that refers to the derivative. Find the derivative to y is equal to x squared, but we are given a specific point. So I wanted to make sure to go through this example. What happens when you have to find the derivative and we are looking for the tangent line at point P when x is equal to 3, y is equal to 9. Now, obviously, again, we start with first principles. We are not going to be using first principles in our Unit 10, Module 2, but this test is all about either substituting directly and manipulating the algebra or using first principles, and we will be very clear on what we're asking you. So instead of x squared, f of x plus h gives me x plus h squared. We have to remember that that is equivalent to x plus h times x plus h, which is x squared plus 2xh plus h squared. So I hope by this point, now that you're in grade 12, you're not scared of algebra and variables. Now we can simplify the numerator, and you'll notice that this x squared eliminates with that x squared. So we have 2xh plus h squared all over h. All remaining terms in the numerator, you will notice, contain an h. So I'm going to take my blue highlighter and just highlight all of my h's so I can factor a greatest common factor of h out of the numerator. Now that h cancels with the h in the denominator, so I'm left with the limit as h approaches 0 of 2x plus h. Now I can simply substitute 0 for an h, 0 for the h in the equation. That is called applying the limit. So my slope of the tangent line at x is equal to 3 is 2x. Now, sorry, the slope of the tangent line is 2x. When I substitute 3 into the equation, because remember I was given this point 3 over 9, so when you substitute x is equal to 3 into the equation, that tells me the slope of the tangent line is 6. So we can go back to grade 9 math. Now that we know that the slope is 6 and the point that we were given was 3, 9, I'm going to substitute my slope into the equation, and I'm going to substitute my x and y point that I've been given into my linear equation. You could also do this with y is equal to mx plus b. I chose point slope form. And you can manipulate the algebra to come up with an equation in standard form. So the equation of the tangent to y is equal to x squared at the point 3, 9 is this equation. Tangent lines are always linear lines, straight lines. So this was a two-step process. We first had to find the derivative, plug the point we were given to find the slope of that derivative function, and then use the slope and the point to come up with the equation of the tangent line. I'm going to give another example of that in a second. So you can see how in calculus we're constantly reaching back to our skills from junior grade levels. So find the slope of the tangent to each of the following at the given point. Here we have a straightforward quadratic equation, but we are given the point when x is equal to 1. So this is another way of solving. I can directly apply this x is equal to 1 for my x in the equation. Sorry, everyone, give me 1 second. I'll be right